Alrighty then, folks. We do a little mic check here. We check on the other computer. Oh man, we can hear ourselves beautifully. Wow, my hair looks a little bizarre today. That's okay. That is alright. It's not that important. Alright, we got our level 12 skeleton up. We got our code right here, ready to go. Everything seems perfectly viewable when you look at it on a larger screen than the one that I have for checking how stuff is going, which is great. And we're gonna go over so our audio will play appropriately. How about that? Hope you guys are all having a wonderful evening. It is a cool but not super cold Sunday evening. And I'm a little sore. I went golfing today. Scored all right as far as I'm concerned. I'm not very consistent yet. But I made some good contact. My last hole, my hole 18 was pretty good. So I was feeling pretty good about that. Back's a little sore from it though. And one of the days this week I have to take the day off, so I need to figure out if I want that to be earlier in the week or later in the week. TBD. Got to figure out when I've got important meetings and when I don't. Looks like if I wanted to take tomorrow off, that would be... Nah. Yeah, maybe I should... Yeah, maybe Tuesday's the right time for that. Unclear. Alright, well... About 30 seconds until we get kicked off here. Let's click the button, because that makes this feel good. I know I don't have a ton of engaging content. I hope the problem tonight is hard, but not that hard. I'm kind of tired. It'd be nice to go to sleep. I just started playing Crypt of the Necrodancer, actually, which has been very fun, but a little bit difficult. I think I'd like playing it on computer more than I like playing it on Switch, but I'm playing it on Switch because I need something to play at bed. Here we go. Day 12, hill climbing algorithm. You try contacting the elves using your handheld device, but the river you're following must be too low to get a decent signal. You ask the device for a height map of the surrounding area, your puzzle input. The height map shows the local area from above broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest elevation, B is the next lowest, and so on up to the highest elevation Z. Also included on the height map are marks for your current position, S, and the location that you should get the best signal, E. Your current position, S, has elevation A, and the location that you should get the best signal, E, has elevation Z. You'd like to reach E, but to save energy, you should do it in as few steps as possible. During each step, you could move exactly one square up, down, left, or right. To avoid needing to get out of your climbing gear, the elevation of the destination square can be at most one higher than the elevation of your current square. That is, if your current elevation is M, you could step to elevation N, but not to elevation O. This also means that the elevation of the destination square can be much lower than the elevation of your current square. Okay. Yeah, so here, you could start in the top left corner, your goal is near the middle. You could start by moving down or right, but eventually you need to head towards the E at the bottom. From there, you can spiral around to the goal. So S, A, B, C, 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 D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, W, X. Wait, but then how do we... X, 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 Y, Z, there. Got it. In the above diagram, the symbols indicate where the path exits, up, down, left, right, blah, blah, blah. The location in this path reaches the goal in 31 steps, the fewest possible. What is the fewest steps required to move from your current position to the location that should get you the best signal? Get your puzzle input. Oh, what is throws? It just tells you that, like, the program may error in a certain fashion. Let's get our input here. Let's try this first. So we want like a list of lists, basically. We want list, okay, integer, grid equals new array list. String line equals scanner dot next line. Grid dot add new array list. Is that right? And in fact, list integer this line equals new array list. And we can add this at the bottom. This line. For int I equals 0, I is less than line dot length plus plus I. I want, oh, and let's look up the ASCII table real quick. ASCII table. I hope that answers your question. Average person 32. The ASCII table suggests that lowercase a is 97. So if character current equals line dot char at I, if current car is S, else if current car is E, else. So in the normal case, int line count equals 0. Trying to think about how best to model this data. I'm gonna pause for a second and think about that. You're starting a Unity C# course and blown away by the fact they don't understand a damn thing. And this is Java, fair enough. Basically the gist is I'm trying to solve this problem. So basically you're given a grid, each of the height, like A is a height, B is one higher, C is one higher, etc. And you want to be able to like find a path where you're only taking at most one step up at once. So let's see. And then we want like a int what do we want to call this? Start line equals minus 1. Int end line equals -1. We want int start index equals -1. Int end index equals -1. So if it's S, then we want start line equals line count. Start index equals I. And then we want to like put, yeah. And for this one, end line equals line count, end index equals I, and then we want to put it in. So then we would want this line dot add for the start 0. This line dot add, this should be 25 because it's Z, right? And then for the rest of them, we basically want to go this line dot add. We want to represent current car as an int. Then we want to subtract 97. I think that should be correct. So that'll parse all the input. And then at the end, we should have the start index and the end index. And we basically then want to seek. Okay, cool. And the other thing we need to do at the end of this is we need to, for blah, 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 blah. We need to line count plus and grid.add this line, which that should be better. So now we should be good. So now we need to have a small path finding algorithm, which let me think. I think we can do this recursively. Yeah, I think we can probably use a priority queue for this. Is that right? Yes. Okay, cool. So priority queue. And let's look up how Java priority queues work. Priority queue. An unbounded queue based on a priority heap. The elements of the priority queue are ordered according to their natural ordering by a comparator. Height of the queue is the least element with respect to the specified ordering. So I need a little class to help me do this. So I need private static class seek point int x int y. Actually, let's call it int line int index int steps so far. There we go. Private int index, private int steps so far. Let's not make these private. We can just accept the fact that I'm going to be touching these, and the class is private, so we're fine. Blah blah blah. This dot line equals line. This dot index equals index. And then we're creating this so that we can have a comparator. This dot step so far equals step so far. And then when we compare these, returns the comparator, use the order of the elements. We can create it with the comparator. And when we go to comparators calls compare on the two things. So we want Java override compare. Java override object compare. Override compare to, is that what we're looking for? We did this in a previous level. Let's see if it's, is it in this one? Compare, no. This one? No. Where did we do the compare to? Nope. Okay, here, let's Control Shift F, compare, does this look right? Let's see. New comparator. Okay, we can just shove the comparator in there. Cool. So how do we construct, we gotta go back. How do we construct this? Takes a collection, initial capacity, priority queue, initial capacity comparator. That's probably what we want. If we, 1 second. Yeah. So priority queue, seek point, queue equals new priority queue, new comparator seek point, return 01 dot, don't want this to be private, I guess. Static class seek point steps so far minus 02 dot step so far. That's probably mad because that's a 0. So that's probably fine. Don't I ever doubt code while writing it? Well, usually I just go ahead and write whatever seems to make sense, and then if it doesn't work, it'll tell me. Don't get it twisted. So now we want q dot add new seek point, and we want start index. We want start line, start index, start line, start index, and the step so far is 0. And then we want int min. In fact, we don't even have to. We can just. We don't even have to. We can just while true this. We don't even have to tell it otherwise. So while true. Nope. Seek point current point equals q dot peak poll. Does poll remove it? What is it? Poll retrieves and removes the head of the queue. Wonderful. That senior level knowledge, definitely not there yet. That's fair enough. I'm actually a staff software engineer, so reasonable enough. That's a lot of programming is getting comfortable enough that you can do stuff without really having to think, and then recognizing that that's the point of like, as long as you can figure out when to think and when you don't have to think, like you're gravy. It's fine. If current point, headed to bed, sweetheart. Good night.
Night.
Have a good night.
Good luck.
Love you. Thank you. And I'll throw new runtime exception. The queue ran out, and let's make a little sad face. So that should never happen, but we have that just to know what's going on there. Why are you mad? Unreachable statement. Okay, cool. So let's see. Now we want to like get the 4 next. So first of all, if current point dot line equals end line and current point dot index equals current equals end index, right? End index, then we're done. So then we can just print out min steps taken is this plus current point dot step so far. Wonderful. And then when we do this, we break. Otherwise, what we're going to do is if current point dot what's dot line doing? Oh, it's just grabbing the it just grabs the property of the seek point. Basically what I'm using this is I basically have an object that encapsulates, okay, where in the grid are we and how far have we gotten? If we're where we're supposed to be, then just break and tell me how long it took you to get there. Otherwise what we're gonna do is we're gonna, like, line is like X. Actually line is like Y and index is like X. But if I call them X and Y, then it like gets weird. So if I just call them line and index, I know what's going on. Cool, so now, basically what we want to do is we want to get to the 4 adjacent points. So current point dot line is not equal to is greater than 0. Then that means that we can go 1 point above. And let's see. So we want grid dot get current point dot line -1 dot get, why are we, probably because of that, dot get current point dot index. There we go. That's actually what I'm looking for. Is less than. Here we go. Let's make this a little bit more readable. So basically, if the current point is at most 2 higher, let's put another paren here to make this a little easier to read. Is less than grid dot get current point dot line dot get current point dot index plus 2. So as long as we're not stepping up by 2, then we want q dot add I guess we could make it so that our compare is a little bit better. Hey Hippoism, we're doing a little bit of programming right now. Q dot add new seek point current point dot line -1 current point dot index current point dot step so far +1. Okay, let's make this readable now, why don't we? Oh yeah, look at that, so much better. Haha. Now we want to do this again, but we want to do it for one lower. Is less than grid dot size? Is that right? -1. That should be right. And +1. Then we want to do +1. There we go. And we're probably missing that here too. And so now we need to do the same thing, but for the left. So if index is less than grid.get 0.size -1. Although I actually we just want it, it's greater than 0. And this -1. This index -1, step so far +1. Fantastic. And then I think we just have to do this one more time, but we want this to actually look more like this. And we want it grid.get 0.size -1. And current point +1. And current point +1. I think that should do it. Let's run it on the test input and see what happens. We have a bug somewhere in here, I'm sure of it. So it's thinking. Int nodes processed equals 0. If debug, which we're going to set to true, system.out.println nodes processed plus nodes processed. We want a private static final boolean debug equals true. And then we want to stop and rerun this so we can see what's going on. Stop and rerun. Finished with exit code -1? You didn't print anything. Oh, well, we didn't tell nodes process to increment, so fair enough. Nodes processed ++. And system.out.println q size plus q.size. Wonderful. And we pulled, yeah, great. And let's do this every 1,000. Okay, cool. So every 1,000 lines is going to tell us what's going on. Let's stop. Let's see what's going on. Okay, this is obviously way too many. So we've got some bug here. So let's debug and figure out what's going on. Okay, so seek point equals. So first of all, let's figure out what it should be. We start at what should be 0, 0. Start line 0. Start index is 0. I'm looking for 2, 5. Is that right? 2, 0, 1, 2, 3, 4, 5. Yes. So we're grabbing the points correctly. So let's check out the seek point that we get. Where is current point? Current point is 0, has taken 0 steps so far, and it's 0. So we're not at null, which is great. So this is false, so we're fine. The line is not, so there's no way for us to go up a row, so that's fine. We can go down a row, so let's go down. So let's see, if we went down a row, we'd still be at A, which is great. And so let's see, is this computing is true or false? It's not telling us yet. Okay, so great. So the queue now has Line 1, index 0. Great. Current point on index is not greater than 0, so we can go to the left. We're going to insert one to the right if we can. And can we go to the right? We also can, so we're great. Okay, cool. So we're probably also like retraversing the grid a lot. So let's make another. Let's make another thing here, so that we don't do that. Boolean array of arrays. Seen so far equals new Boolean, and this is going to be grid.size, and this is going to be grid.get0.size. And then we want seen so far. They should all be false. But because we're going to input this one, seen so far of our first one should be true. Seen so far, start index. Sorry, this should be start line. Start index equals true. And so if this and this. If this and here, we'll insert it here. Seen so far, current point dot line, current point dot index. This should be line -1. And let's put an and we want it to have not been seen so far. So we want this, and we need to copy this here, except this needs to be now +1, and then we need to copy it here. This needs to be this, and this needs to be -1, and then this we can just copy here and to make it +1, and now at least we shouldn't be so huge. So we'll have another issue, but let's try running it and see what happens. When we add it, of course that's not doing anything. Seen so far, this equals true. We need to copy this, and then we'll edit it per 2, 3. So now what we're doing is we're updating whether or not we've seen the current line, so that we aren't touching points more than once, because we shouldn't be able to. -1, and then this is that same thing, but +1. Run it again. What do you know? When you're not allowed to backtrack, you save a lot of time. Fantastic. So now if we run this on the real input, this input's way bigger. Run it again. 528. Are we right? We are. Let's do part 2. Part 2. As you walk up the hill, you suspect that the elves will want to turn this into a hiking trail. The beginning isn't very scenic, though. Perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start as low as possible, elevation A. The goal is still the square marked E. However, the trail should still be direct, taking the fewest steps to reach its goal. So you'll need to find the shortest path from any square at elevation A to the square marked E. Again, consider the example from above, blah blah blah. Now there are 6 choices for the starting position, 5 marked A plus a square marked S, that counts as being at elevation A. If you start at the bottom left square, you can reach the goal most quickly. This path reaches the goal in only 29 steps, the fewest possible. What is the fewest steps required to move starting from any square with elevation A to the location that should get to the best signal? Okay, so we basically just want to take what we did in part 1 and abstract that out into a helper function. So let's see if we can do that. The things that we need so far are private, static, min steps. This should return an int. This takes in a list of integer grid. It takes in int start index, takes in int end index, takes in int start line. Sorry, this should go int start line here. Let's put this in an order that's going to make sense. Int end line, wonderful. What else does it need? Let's find out by copying and pasting this. So we want min steps. In fact, we can just copy this. Blah, 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 etc., etc., etc. We're gonna put the thing there, so we should be fine. So now we want this. So now we want int min steps equals min steps this. Let's get rid of the int this. That should, in theory, be better. Okay, and we don't want this type either. So just grid, start line, end line, index, whatever. Let's take all of this stuff and put it in there and then see what happens. So this now goes into our helper function. Is anything undefined in here? Not really. And then instead of, we just want to return this. Return, except let's take this line and put it somewhere higher up for part 1 so that's not broken. There we go. And then this part instead just needs to be return this, which then is automatically going to break itself. Wonderful. We should be fine. So now we just need to call this with different values for start line, start index, end line, end index. Okay, and this instead needs to be min steps. Wonderful. So that part should still be fine if we run it. Fantastic. 528. You'll love to see it. So part 2, we want to read in the grid just as we did before. This. Fantastic. Oh crap. This needs to go here. Okay, great. So we've read it all in. We actually don't need start index or end. Well, we do need end index. We just don't need start index. So let's get rid of the start index. End index and end line can stay there, etc. Now we want integer min steps equals integer dot max value for int I equals 0, I is less than grid dot size. Let's call this line actually, just to keep things plus plus line for int index equals 0, index less than grid dot get 0 dot size plus plus index if grid dot get line dot get index equals 0. So if we're starting at the lowest elevation, then int min for this location equals min steps grid line index and line end index. Min steps equals math dot min steps min for this location. System dot out and then min possible steps is min steps. So now if we go to this, we set it to part 2. Part 2, lovely. Run it. Oh no. Something about my algorithm not work? What's going on? So let's go back to min steps. So part 1 worked, right? Part 1. Great, 528. Let's go to this one. What is the fewest steps required to move from starting from any square with elevation A to the location that should get the best signal? One second. Goal is still marked E. However, the trail should still be direct, taking the fewest steps possible. So you need to find the shortest path from any square at elevation A to the again marked E. Some of them might not work, I guess. Like, it might be impossible. Let's look at our data real quick. See if there are any A's that are like all by themselves. I suppose I could also just build this as like a descent from the end. It's a cool little like topological map over here, which is pretty neat. Also interesting, so 7,000, and now if we go part 2, does this fail after the same 7,000 iterations or so? Huh. Why aren't you mad? Let's go back to here. And we create the scene so far here, right? Yeah. It's brand new. So let's debug real quick. Just like here, I guess. Debug it. Cool, so we're here. And if we step up and then go down, so 526, so we play. We look at scene so far, it's all false except for one thing. So if we step up, then we failed again. Okay, cool. So if current point equals null, let's make a note. The current point is doesn't have a path to the top, e.g. too deep a gully, no smooth route out, return integer dot max value. Okay, now let's run and see if we get an answer. Min possible steps 522. Let's see if that's the right answer. I'm curious. That is the right answer. Okay, so I guess we're just gonna assume that I didn't screw up there, and we'll be proven wrong there. Okay, let's return. Let's see how we did. Personal stats 1700 and 1951. Not the worst. Not our best, but it's amazing that we've gotten exactly 1700th twice in the last 3 days. Still hoping to crack the top 1,000. That's usually the days that we're proud of, but apparently this is about where we belong. So no huge qualms there. Let's go to the leaderboard, see if anybody else is playing. Yeah, nobody's tried tonight's. We're building an insurmountable lead. And similarly so there. All right, well, let's go back and add this real quick, which shouldn't be too bad today, especially as compared with yesterday. So day 12, this, nothing. You're following Trulo to get to decent signal. Your puzzle input. Oh, it's because we're looking at part 2. Let's see. So Z needs to be highlighted, B needs to be highlighted, and A needs to be highlighted. By highlighted, I mean code. Also, current position S, location, get the best signal, E, your current position S, no, escape, has elevation A, location with the best signal, E, has elevation Z. Wonderful. You'd like to reach E, but to save energy, you should do it in bold, as few steps as possible. Wonderful. During each step, you can move 1 square up or down. We're looking for the phrase at most 1 higher. At most 1 higher. Wonderful. Then whatever. That is, if your current elevation is M, you can step to elevation N, but not to elevation O. for example, this. We're going to add some extra spaces because that's how we like it. Here, your top left corner is this. Move towards the E at the bottom. And again, we're just going to make copious space because that makes it easier to mess with. So we go back up. In the diagram above, indicates the path. All of these are code for some reason. I mean, I get it, but it's tedious. Best signal is still E, and dot marks unvisited locations. This path reaches the goal in 31 steps, the fewest possible. What is the fewest possible steps to acquire the best signal? Your answer was 528. Wonderful. Part 2. So you walk up the hill, blah, blah, blah. E, A, and then all of this. Any square at elevation A gets bolded. Elevation A. Again, consider the sample from above. Can't do. Now there are 6 choices. 5 marked A, plus the square marked S that counts as being at elevation A. If you start at the bottom left square, you can reach the goal most quickly. That makes sense. It just skips a bunch of the path. This path reaches the goal in only 29 steps. Fewest possible was the fewest possible number of steps to get to elevation A. Your answer was 522. Great, complete. So let's go comment the code. Let's get rid of this unneeded import. Read in the grid. Keeping track of the start and end points. Okay, and converting the characters into their implicit heights. Wonderful. Call helper function for start point, return min steps. That's an unnecessary comment, but I wrote it. This needs to be the same comment as this, except it only keeps track of the endpoint. Keeping track of endpoint and converting characters into their implicit heights. Calls helper function for each possible starting point, keeping track of the one that has the lowest value. Man, this is probably not a great solution, but it's great. So now we can just go to min steps, and this. Whoop, there we go. Let's delete that real quick and then get it right. Wonderful. When a grid, a place to start, and a place to end, searches for the shortest path from start to end where the value in grid in adjacent steps can increment by at most 1. Returns how many steps that path takes. Cool. So yeah, so this is not the best solution in the world, but let's talk it through real quick. All right, let's describe what's going on, and let's full screen this so we can see what's going on. So what we want to do is we're given a grid like this giant grid, and we start at some place that has Control F for S. It should be here. So we start here at S, and we want to eventually get to E, which is over here. And we can go up, down, left, or right, but we can only go if the value of the square that we're going to is at most 1 higher. So for example, here we're at A, we can't go to where the C's are. Like, that's not allowed, but we can step to the other A or the other A, that's fine. And we can go one higher if we want. So for example, this A is next to a B, so then it can go up to C. That's fine. You can go A to B to C, but you can't go A to C directly. So given this grid, our first thing is just starting at S and ending at E with those constraints, which is the minimum possible path. And so, oh, we should add this to the comment. Uses breadth first search. Cool. So what we do is we read in the grid and we turn all the letters into numbers. So S gets 0, A gets 0, B gets 1, C gets 2, etc. all the way up to Z gets 25, and the uppercase E where we're ending gets 25. And then what we do is we keep track of also of the start point and the end point. And then what we do is we call this helper function. Now what this helper function does is given a start point and an end point and a grid of values, it does breadth first search. So it creates a priority queue, which is a thing where the front of it has the minimum value. And we use the comparator of how many steps have we taken so far. So we're breadth first searching our way through. And we use this class seek point, which just has the point where we are and how many steps it's taken to keep track of what's going on. And then basically what we do is we put the point we start at in the queue, and then we check all of its neighbors and see if any of its neighbors we would be allowed to go to. And also what we do is we don't allow ourselves to backtrack. So we use seen so far. So what we do is we pull a point out of the queue, and that'll be the point which has taken the fewest steps so far. If there is no current point, then we just return that it was like there's no path from the beginning to the end, because otherwise we will have returned already. Then what we do is if this current point is the place that we're trying to go to, then we just return how many steps it took to get here. Great. Otherwise, we see if we can go up, we see if we can go down, we see if we can go left, we see if we can go right. If we can, we put those points in the grid, and we also say that we've seen those points so far so that those points don't get inserted multiple times. Because we do things in order of breadth first search, there's no way that we're going to be trying to insert those points again later with a lower value. Otherwise, we would need to do something more complicated for this seen so far variable. This will continue to run just for forever until the queue runs out of things, which it will do eventually because it can only put in every element at most once, so it can run at most the number of loops of the size of the grid. And it will return either when it runs out of elements or when we've hit the point. So that gives part one. For part two, we're basically trying to do the same thing. We read in the grid, but now instead of just starting at S, we're trying to start at S or any place that says A. So what we do is we just ran our solution there on every one of those points. Now, in theory, what we could do better is just run a breadth first search from the top to the bottom and try and get the minimum number of steps from the top to any given point. No, that doesn't quite work because we'd have to like run the reverse logic, which doesn't really track. I mean, you could. Basically, you're only allowed to step down one, but you can step up as much as you want, and then you expect to go in the reverse direction on the trail. That would be fine. So you could just like flood the whole grid that way from the end to the beginning. That would be all right. Probably be a lot faster too. And then what you do is you just take the minimum value where the value is A, like you just run those two things against each other. What we did is a lot dumber. We basically just, for every point A, ran that same breadth first search again. And because there's not that many A's and it runs real fast and our computer's real fast, and this grid's only so big, you know, it's 41 by, oh, how long is this line? 181. That ended up 41 by 181 is 400, like 800 maybe, as an upper bound. So is that right? It's 8,000. Is that right? If we control A this, yeah, it's 7,400 characters. So running that thing 7,000 times still ended up being relatively quick. Not the fastest thing in the world. In fact, let's add a comment. Uses the naive solution of there should only be one I. It's just the I with two dots of running part one over and over again. A better solution may be building the minimum path starting from the exit and using reverse conditional logic. e.g. can step down at most a height of once for the whole grid. Then you can just get the solution in a single pass, but our input was only 1,000 in size, so it still works as is. Great. So yeah, we could have done a lot better by just running it once and then just parsing through to get the answers. But luckily, runtime is not a component to the solution. It just matters that you get the answer. So we're going to be leaving this as is. Let's go ahead and commit this, and then we're going to log off for the night. Commit day 12 solution, and all of that is there. Commit and push. We're going to push anyways. Let's remove the structure. Push. Okay, are we good? Are we fine? We appear to be fine. All right. Well, in that case, I'm going to call it a night. Appreciate you folks being here. I'll see you guys tomorrow.